Good evening to all. I am Debarun Pal. I am a PhD student from Indian Statistical Institute, Kolkata. So first of all, I would like to thank the organizer to give me the opportunity to present my work over here. And today I'll be discussing about primordial gravitational waves, which can be probed as a dark matter and a leptogenesis in the future gravitational waves missions. So my today's talk will be mainly based on the statistical analysis technique by which we can probe this dark matter and the leptogenesis scenario in the future gravitational waves missions. So my talk is based on this paper, and they are my collaborator, and Anish is here over. So yeah. So this is the very well-known diagram for the evolution of our universe, depicting the evolution starting from the Big Bang to the present day. And my focus is mainly at the early universe cosmology. So especially we know from the inflation, basically it generates the primordial fluctuation, and from there we can we get some gravitational wave spectrums. Now, after its generation, the gravitational wave travels throughout our universe in a completely unperturbed way, unlike the cosmic microwave backgrounds. And that is why it becomes a very good tracer for our early universe, and not only that, it can becomes a very good and unique probe for the heavy relics particles like the dark matters and etc. And that is why today this gravitational wave background can as a very unique window to probe the early universe and some other cosmical relics. Okay, so whenever we are discussing about the early universe cosmology, there is some basic difficulties in probing them, because BBN says that the energy scale is nearly 1 mega electron volt, whereas CMB predicts the maximum scale of the inflation is nearly 10 to the 14 or 16 GeV. So at least in terms of the energy, there is a huge gap over here. So basically, this reheating can be maybe a possible solution linking these two phases, the inflationary and radiation domination epoch. And this reheating epoch and the mechanism of reheating can be, there are many possible ways. But today I will be mainly discussing about the gravitational reheating scenario. So where this inflation scattering produces some daughter particles via some gravitons, etc. Now the question is, why do I consider this gravitational reheating process over here? So basically, we know from the various cosmological and astrophysical observation that the dark matter should interact with the other particles at least via the gravity. On the other way, there are some heavy relic particles over there which cannot be, may not be easily probed at the Large Hadron Colliders, but they must, or they at least interact with the other particles via this gravity. So that is why this gravity-mediated channel is very, very unique and natural, and that is why we have considered this reheating phenomena, which is a gravity-mediated process, through some gravity-mediated process, the gravitational reheating one. So based on this gravitational reheating scenario, there are a couple of works, several works has been done, starting from the particle production to the to investigated their signatures at the primordial gravitational wave background. So I'm sorry. So here we have done in our paper some statistical analysis. If we detect the primordial gravitational wave background, if it is primordial gravitational wave background detected by the future gravitational wave missions. So basically, since it is a era of precessional cosmology, so whenever we are trying to probe or trying to probe some particular parameter, so we need to talk about the uncertainty associated with each of the parameters. So that is why in our work we have discussed some particular statistical analysis to reveal those uncertainty, and as well as I will discuss how this total structure are able to probe the dark matter parameter space, the mass scales of the dark matter, and gravitational leptogenesis scenario. So this is the outline of my today's discussion, where I will be mainly discussing about this signature of each of the parameters on the gravitational wave background. Then I will move on to the signal to noise ratio calculations and some two statistical techniques, the Fisher forecast analysis and the Markov chain Monte Carlo analysis. I will discuss it later on. And finally, I will show how this scenario are able to probe the dark matter parameter space and the gravitational leptogenesis scenario. Yeah. So as I have mentioned, I will stick on the gravitational reheating scenario. So here we have considered a particular inflation potential, but the behavior of this inflation potential near its minima is 5 to the power n. N is an exponent. So this whole analysis it's mostly independent in the form of the inflation potential. Now, depending on this n, the equation of state during the epoch of reheating can be represented in this fashion. Now, additionally, we have considered our non-minimal coupling between this gravity and some standard model sector, and xi is the non-minimal coupling parameter. And on top of them, we have considered the tensor spectral index as a free parameter and the scale of the inflation. So basically, in our hand, we have 4 parameters: equation of state, non-minimal coupling parameter, the tensor spectral index, and the scale of the inflation. So let's check what are the signatures at the primordial gravitational background. So the gravitational signal, the spectrum of the gravitational wave can be represented at the present time in this way, for which we have followed this Mohammad Rezul and et al. Papers. And this is the behavior of each of the parameters on this primordial gravitational background. For an example, this represents the behavior of the xi parameter. You can see as we increase this xi, there's some dampening in the signal. This is the behavior of this changing the equation of state. This is for the changing the variation of scale of the inflation, and this is for the tilt. I am changing the tilt over here, and you can find for the some blue tilted spectrum there is some tilt, this dashed line. Now, here you can see for all of this diagram gives some hope that this signal at least can be probed at the sum of the space-based and the ground-based mission, like the BBO, ET, LISA, and etc. So that is why now we just move on whether or we need to properly assess those signals, whether this can be detected at those detectors or not. So that is why we do this signal to noise ratio calculation, and this is nothing but the ratio between the strength of the signal with the noise, where tau represents the total observation time, which for in our analysis we have considered the observation time to be 4 years for all the 4 detectors. Okay, so here we have set the particular detectional threshold for all these 4 detectors, PBO, DESIGO, ET, and LISA is to be equals to 10, and these contours represents this SNR equals to 10, and all the binate positions is representing the region where this SNR is greater than 10. Okay, so here all the colors represent the different detectors, and whole scenario is in the equation of state and the xi plane. And we have drawn this similar thing for the other 2 parameters, right? So this is the time we need to go to do some uncertainty calculation associated with each of the parameter, because we are, if all of the detector are basically trying to probe this particular parameter space. Fine. So to do this, we have considered this Fisher forecast analysis and the Markov chain Monte Carlo analysis, the MCMC analysis. So Fisher forecast analysis basically tells about the uncertainty associated with each of the parameters. So basically it is a fiducial dependent technique. It only tells about the uncertainty, but it does not tell anything about the mean position, the fiducial position. Okay, but the MCMC analysis, it tells about not only the uncertainty associated with the parameter, but also it tells about the mean shifts of the parameters. Okay, so first let us start by the first one, the Fisher forecast analysis. So to do this, we have considered a Gaussian type likelihood function, and these all the symbols represent a very similar meaning. But the point is that here also we have considered the observation time to be 4 years, as we have considered at the SNR calculation, the signal to noise ratio calculations. Fine. So we can construct the Fisher matrix from the likelihood function in this way, and this likelihood from the Fisher matrix we can derive this uncertainty in this way. Basically, this uncertainty is basically nothing but the inverse of this Fisher matrix. Now, on this ground, we have drawn the posterior distribution for these 3 detectors, BBO, DESIGO, and ET, and all the colors represent the different detectors. The interesting thing is that equation of state for all the 3 detectors are in negative correlation with this xi and the nt, and the xi and nt are in the positive correlation for all the 3 detectors. And at the same time, I will try to draw your focus in this black contours. This black contour represent the ET, and you can find the uncertainty for the ET is quite smaller. So that means ET is more promising, and Fisher forecast analysis tells us that the uncertainty associated with the ET is very lesser. That means if in future this signal can be detected by the ET, So there will be this will detect the signal with more tight results, something. So now let's move on to the MCMC analysis. Here also we have considered the same likelihood function, and we run the do this analysis for the same 3 parameters. And here is the posterior distribution. For this, we have considered some mock catalogs, which based on the high SNR value and where this relative uncertainty is less than 1. Yeah, fine. So here also you have find the same correlation pattern as we have got in the Fisher forecast analysis. And this is something the results we have got, obviously depending on the mock catalogs, but all the results suggest that the uncertainty associated with the ET is quite lesser. That means ET is showing the more promising results in our ground. Fine. So till now, whatever we have seen, that so some statistical analysis technique, and we have shown how the statistical analysis technique can be used to probe and to determine the uncertainty for each of the parameter space. So let's move on that how this scenario can be used to probe the dark matter and the gravitational leptogenesis scenario. So to do this, we have considered the 3 Majorana right type neutrino, where this least one serves as a dark matter and the other 2 produces the lepton asymmetries. So let's start by the first one. So we have at the early time, dark matter can be produced in the 2 mechanisms. One from directly from the inflaton scattering, obviously via gravity mediated process, and another via the from the thermal bath. And the contribution on this dark matter abundance can be calculated in this fashion, for which we have considered the Vasubhendu Bormans and et al. Papers. And the resultant contribution of the dark matter abundance is simply the sum of these 2. Yeah. So this is the something which I have got from the SNR calculation. So I am just rushing it down. So here we have found some lower bound on the dark matter parameter space, which is nearly 10 to the power 6 GeV, which coming from the, and we are telling up if the dark matter mass is beyond this 10 to the power 6 GeV, we can detect the mass where this SNR is greater than 10. And all this calculation is based on the 4 years of observation. And at the same time, the gravitational leptogenesis scenario and the gravitational baryon asymmetry for this gravitational production can be represented in this way. And at the same time, if we want to probe this leptogenesis as well as the gravitation as well as the dark matter scenario simultaneously, then we got some upper bound which coming from the underproduction of the baryogenesis. And here we got some typical range 10 to the power 6 to 10 to the power 7 GeV, depending on the scale of the leptogenesis. Fine, so that's all. So here is my conclusion over here. So here I mainly discuss about the parameter space and the signature of the parameter space on the gravitational waves, primordial gravitational waves detectors signals. And then I move on to the signal to noise ratio calculation, and finally the statistical techniques, and all of the statistical technique represent this. ET is more promising compared to the other detectors, means the BBO, Desigat, and LISA. And finally, I have shown there is some scale, we can show that this mechanism are able to probe this dark matter parameter space and the gravitational leptogenesis scenarios. Yeah, thank you.
Thanks, Debarun, for this informative talk. So let's have some quick questions. Okay, so if not, let's thanks all the speakers of the day, and thanks for listening over all the day so patiently. So, okay, let's wrap it up. Thanks.